Hey guys, tonight we are going on a bit of a different kind of trip. We're traveling back. Not just a few years, not to see the dinosaurs, but all the way back. To the very beginning. To a time before time itself even had a name. So, I hope you brought your imagination, and maybe packed a snack, although there won't be anywhere to put it. Also, please remember to wear your most durable conceptual spacesuit for this one. It doesn't need to hold oxygen, because there won't be any, but it does need to handle the mind-bending pressure of witnessing, well, everything. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Your support truly means the world, or in this case, the universe, to me. After you've done that, maybe drop a comment and let me know what city you're listening from, and what time it is for you. It's always a quiet joy to see where our little community is scattered across this spinning globe. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. Alright. Take a deep, slow breath. And another. Where are you? Well, the answer is, nowhere. And everywhere. There is no up or down. No left, no right. Close your eyes, and what you see is a perfect, velvety black. But it's not just dark, it's the absence of light itself. It's not just quiet, it's the absence of sound, of vibration, of anything that could ever make a sound. Time hasn't started its relentless march forward yet. Space, as you know it, doesn't exist. It's the ultimate state of nothingness. A profound, peaceful, and perhaps slightly unnerving void. But wait. In the center of this non-existent space, you sense something. Or rather, you sense the potential for something. It's not an object you can see, because there's no light to see it with. It's a point. A single, infinitesimally small, impossibly dense point. Think of the sharpest pinprick you can imagine, and then shrink it 1 billion times, and 1 billion times more. All the energy, all the matter, all the future stars, galaxies, planets, and even the very laws of physics that will one day govern them, are compressed into this one cosmic seed. It's a bit of a paradox, isn't it? Everything that will ever be, all held within a volume smaller than a single atom. Some call it the singularity. You're floating here, a silent observer, in this pre-cosmic waiting room. How long have you been here? A second? An eternity? The question is meaningless, because the clock hasn't started ticking. And then, it happens. It is not an explosion in the way you might imagine. There is no deafening bang, no fiery shockwave tearing through space. Because, remember, there is no space for it to tear through. Instead, it's an expansion. An unfolding. The point doesn't explode into space, the point becomes space. It's a silent, instantaneous blossoming. In the very first, incomprehensibly tiny fraction of a second, a slice of time so small it has its own name, the Planck time, about 10 to the power of -43 seconds, the 4 fundamental forces of nature that you know today, gravity, electromagnetism, and the strong and weak nuclear forces, were all one unified superforce. The universe is born in perfect, elegant unity. It's a bit like an orchestra before the conductor gives the downbeat, all instruments holding a single, perfect, resonant note. Then, just as quickly, this unity shatters. The forces split apart. Gravity steps out on its own first, like a shy guest leaving a party early. The universe, in a moment of what can only be described as cosmic overenthusiasm, undergoes a period of inflation. It swells from smaller than an atom to larger than a galaxy, faster than the speed of light. This isn't breaking any rules, by the way, it's space-time itself that's expanding, not objects moving through it. A neat little loophole. Now, you're no longer in a void. You are inside a searingly hot, fantastically dense fog. The temperature is trillions of degrees. It's so hot and so dense that atoms can't form. Even protons and neutrons can't hold themselves together. Instead, you are swimming in a chaotic, shimmering soup of fundamental particles, quarks, leptons, gluons, all zipping around and colliding in a frantic, beautiful mess. It's the universe in its toddler phase, full of energy, slightly chaotic, and not yet forming coherent sentences, or, matter. This primordial state is known as the quark-gluon plasma. As you float in this vibrant, thick cosmic soup, a thought might occur to you: what was before the singularity? What lit the fuse for the Big Bang? And this is where science gives a gentle shrug. The honest answer is, we don't know for sure. It's one of the biggest mysteries out there, and a topic where scientific arguments can get, well, let's just say, passionate. Some theories propose a cyclical universe, one that endlessly bangs and crunches, like a cosmic accordion. Others imagine our universe as just one bubble in a vast, frothing multiverse. As of right now, for us, for you, this moment is the true beginning. The first page of the story. The initial flash of creation has passed. The universe continues its relentless expansion, and as it grows, it begins to cool. The frantic energy starts to subside. The cosmic soup is thinning out, its temperature dropping from trillions of degrees to mere billions. The particles are slowing down, getting ready for the next great chapter of creation. The first blinding light of the Big Bang is fading, and a new, different state is about to take hold. A long, quiet period of darkness. The superheated cosmic soup has now cooled enough for the quarks to latch onto each other, forming the first protons and neutrons. For the next few 100,000 years, the universe is a bit like a rowdy playground that's been told to calm down. It's still incredibly hot, thousands of degrees, and it's filled with a thick, glowing fog of charged particles. You're floating in this celestial haze. If you were to hold up your hand, your conceptual hand, of course, you wouldn't be able to see it. Not because it's dark, but because it's too bright, in a strange, oppressive way. Light exists here, in the form of photons, but they can't get very far. Imagine you're in the densest fog you've ever seen. Every time a little particle of light tries to make a break for it, it immediately smacks into a free-floating electron and gets scattered in a random direction. It's a cosmic game of pinball, and the photons are the balls, ricocheting endlessly. The entire universe is opaque. There's no view. There's just this uniform, featureless, pearly glow in every direction. It's a bit claustrophobic, honestly. A universe with no scenery. This period, which lasts for about 380,000 years, is often called the Cosmic Dark Ages. Which is a bit of a misnomer, because it wasn't dark, it was just murky. And frankly, a little boring. After the sheer drama of the Big Bang, the universe settled into a long, uneventful phase of simply expanding and cooling. No stars, no galaxies, just this endless, sweltering fog. But as you drift through this quiet epoch, you can feel a subtle change in the air. The temperature is dropping. Steadily, relentlessly. The expansion is doing its job, stretching everything out, giving it all room to breathe and cool down. The universe is about to cross a critical threshold, dropping to a balmy 3,000 degrees Celsius or so. To you, that sounds absurdly hot, but for the universe, it's the perfect temperature for something magical to happen. At this temperature, the frantic, free-roaming electrons finally lose enough energy to be captured by the protons. They stop their wild dance and settle into stable orbits. It's the cosmic equivalent of a planetary-scale game of musical chairs ending, and everyone has found a partner. Protons and electrons combine to form the very first stable, neutral atoms, mostly hydrogen, with a sprinkle of helium for good measure. This event is called recombination. And in the moment that this happens, everything changes. Suddenly, the pinball machine is switched off. The light-scattering electrons are now neatly tucked away inside atoms. The path for the photons is clear. For the very first time in its history, the universe becomes transparent. The light that was trapped in that cosmic fog is now unleashed, free to travel in straight lines across the cosmos, forever. This is the universe's first light. A silent flash, happening everywhere at once, illuminating the cosmos for the first time. You can finally see. What do you see? A vast, empty, and now truly dark space. The glowing fog has vanished, replaced by an immense, silent darkness, punctuated by this newly released ancient light, which stretches and cools as the universe expands. This primordial light, the afterglow of the Big Bang, is still traveling across the universe today. We can detect it. It's called the cosmic microwave background, or CMB. It's the oldest picture of the universe we will ever have. It's like finding a baby photo of the entire cosmos. And here's a funny thing, if you've ever seen static on an old analog TV, a tiny percentage of that snow was interference from this very light, the 13.8 billion-year-old echo of the moment the universe switched from opaque to transparent. You were literally seeing a remnant of creation in your living room. So now you're floating in a vast, dark, and transparent universe. It's filled with enormous, drifting clouds of neutral hydrogen and helium gas. It's quiet. Very quiet. The overture is over. The stage is set. But the main actors haven't arrived yet. There are no stars to warm the void. No planets. No galaxies. Just gas. Mile after mile, light year after light year of cold, dark gas. This is the true cosmic dark age. But it's not an empty darkness. It's a darkness full of potential. Because these gas clouds aren't perfectly uniform. Thanks to those tiny quantum fluctuations back in the Big Bang, some areas are just a tiny, tiny bit denser than others. You can't see them, but they're there. A slightly thicker wisp of hydrogen here, a slightly sparser patch there. These imperfections are the seeds of everything that is to come. Of course, the transition from this neutral gas to the star-filled cosmos we know wasn't instantaneous. Scientists are still actively debating the exact timeline of what happened next, an era called the epoch of reionization. When did the very first stars ignite and start pumping out enough radiation to strip the electrons off those neutral atoms again, lighting up the universe in a new way? Was it a quick process, or did it happen in fits and starts over hundreds of millions of years? The James Webb Space Telescope is peering into this very era right now, trying to give us clearer answers. It's one of those wonderful areas of science where the map is still being drawn. But for you, floating here in the profound blackness, you don't need to worry about the specific timeline. All you can feel is a new player entering the game. It was there all along, right from the very beginning, but its influence was drowned out by the heat and chaos. Now, in the cold and the quiet, its voice is becoming clear. It's a gentle, persistent, and irresistible pull. The force of gravity. And it's starting to whisper to those slightly denser clouds of gas, coaxing them, pulling them together, getting ready to build something spectacular. You are adrift in an ocean of silent, cold darkness. The grand flash of recombination is a distant memory, its light now streaking across the expanding cosmos, leaving behind a profound stillness. For millions upon millions of years, this is the state of the universe. It's a bit like a pristine, untouched canvas, waiting for the artist to make the first stroke. The universe is expanding, yes, but on a local level, a new force is beginning to assert its dominance. Gravity. It's a patient, subtle force. You can't see it, but you can feel its effects all around you. Remember those infinitesimally tiny density fluctuations in the primordial gas? Gravity has been working on them, tirelessly, for eons. Imagine a vast, almost perfectly smooth cloud of hydrogen and helium. Gravity finds the one spot that is just 1/1,000,000% denser than the area next to it and starts to pull. Ever so gently. At first, nothing seems to happen. The process is agonizingly slow. Atoms are drawn towards these slightly denser regions, but the distances are vast, and the pull is weak. It's like trying to gather dust bunnies from across a football field using only static electricity. But gravity has one thing on its side, time. And it has all the time in the world. Slowly, over tens of millions of years, the process accelerates. As a clump of gas pulls in more atoms, its own gravitational pull gets stronger. This creates a feedback loop. More mass means more gravity, which means it can pull in even more mass, even faster. The tiny, insignificant whispers of gravity are now becoming insistent shouts. You can see it now. The vast, uniform clouds are starting to curdle. They are fragmenting into smaller, denser filaments and clumps. The cosmic fog is condensing into a delicate, sprawling network of gas, like a spiderweb stretching across the void. Astronomers call this the cosmic web. The long, thin strands are the filaments, and at the intersections, where the filaments meet, you find the real action. These are the nodes, the galactic superclusters in the making. And within these filaments, smaller knots of gas are collapsing in on themselves. Let's focus on one of these knots. It's a colossal sphere of hydrogen gas, many light years across, slowly rotating as it collapses under its own weight. This is a protostar, or rather, a proto-protostar. It's the very first generation of stars to be born. These are the population 3 stars, as they're technically known. And they are nothing like the stars you're familiar with. Because they are formed from the pure, pristine hydrogen and helium forged in the Big Bang, they lack any of the heavier elements, the metals, as astronomers call anything heavier than helium. This purity has a profound effect. Heavy elements are actually very good at radiating away heat, which helps a collapsing gas cloud to cool down and fragment into smaller stars. Without them, these first-generation clouds can't cool down efficiently. They just get hotter and hotter as they collapse, meaning they need a much larger amount of mass to finally ignite. So, the first stars are not quaint little suns. They are monsters. Absolute behemoths. Hundreds, perhaps even thousands of times more massive than our own Sunday. As the gas cloud collapses, the pressure and temperature at its core skyrocket. It gets hotter and hotter, reaching millions of degrees. You can see the center of the cloud begin to glow, first a dull red, then a brighter orange, then a brilliant, searing white. And then, a critical point is reached. The core becomes so hot and so dense that nuclear fusion ignites. Hydrogen atoms are slammed together with such incredible force that they fuse to become helium, releasing a tremendous burst of energy in the process. A star is born. The first light since recombination now floods the dark universe. After maybe 100 or 200 million years of absolute blackness, a single point of brilliant, blue-white light pierces the void. Then another. And another. Across the cosmic web, these stellar titans are roaring to life, one by one. The cosmic dark ages are officially over. The universe is being lit up again, not by an ancient afterglow, but by new, fresh, brilliant stars. These first stars burn incredibly hot and live fast, die young. Their immense mass means they burn through their nuclear fuel at a furious rate. While our sun will live for about 10 billion years, these giants last for only a few million. It's a short and glorious life. But their death is just as important as their birth. When one of these behemoths runs out of fuel, its core collapses catastrophically, and it detonates in an explosion of unimaginable power, a supernova. Or, in this case, something even more powerful, a hypernova. This explosion is so violent that it forges new, heavier elements for the first time in cosmic history. The hydrogen and helium from the Big Bang are cooked into carbon, oxygen, silicon, iron, all the elements that were missing before. These newly forged elements are then blasted out into space, seeding the surrounding gas clouds. This is a pivotal moment. The universe is no longer just hydrogen and helium. It's been enriched. It's been contaminated in the best possible way. This stellar ash, this stardust, will become the raw material for the next generation of stars, for planets, and eventually, for you. Of course, the exact nature of these first stars is still a subject of intense research. How massive were they really? Did they form alone, or in small clusters? Answering this is tricky, because they are long gone. We can't observe them directly. It's a bit like trying to understand the first living organism by only studying modern animals. You have to infer what happened from the clues left behind. Scientists use computer simulations and study the chemical composition of the oldest known stars today to piece together the story of their long-lost ancestors. For now, you float among these newly enriched clouds. The first stars have lived, died, and scattered their guts across the cosmos. The universe is no longer pristine. It's now seeded with the building blocks of complexity. And gravity, the patient sculptor, isn't done yet. It's taking these larger, enriched clouds of gas and dust and starting to pull them together into something even grander. Something on a scale that will soon dwarf even these monstrous first stars. The era of galaxies is about to begin. The deaths of the first stars were not an end, but a spectacular new beginning. You are floating in a cosmos that is now seasoned with new ingredients. The vast clouds of gas are no longer just pure hydrogen and helium, they are now laced with carbon, oxygen, nitrogen, and iron. This cosmic recycling program is in full swing, and it's about to get industrial. Gravity continues its work, but now it's operating on a much grander scale. It's not just pulling together gas to form individual stars, but pulling together enormous regions of gas, dust, and even the mysterious, invisible stuff we call dark matter, into gargantuan structures. These are the proto-galaxies. At first, they are messy, chaotic collections. Imagine a cosmic construction site. Clumps of star-forming gas, entire clusters of the second generation of stars, and swirling streams of enriched material are all being drawn together by their mutual gravity. They smash into each other, merge, and churn in a beautiful, violent dance. These are not the elegant, pinwheel spirals you see in photos. These early galaxies are clumpy, irregular, and hyperactive. They are like cosmic teenagers, awkward, full of explosive energy, and constantly changing. You drift towards one of these nascent galaxies. It's a hive of activity. Star formation is happening at a furious pace, far more intense than in a modern galaxy like our Milky Way. These are known as starburst galaxies. The gas is so dense and turbulent that it's collapsing into new stars everywhere you look. The galaxy glows with the brilliant blue light of young, massive stars. Supernova explosions flash like strobing lights at a rave, constantly churning the gas and seeding it with even more heavy elements. The universe has become a factory. A galaxy-sized factory for making stars and elements. It's here that the alchemy pioneered by the first stars is perfected. Successive generations of stars live and die, each one contributing its own unique blend of elements to the cosmic soup. Smaller stars, like our future sun, are good at making elements like carbon and nitrogen. Massive stars are the champions of creating oxygen and silicon, and their explosive deaths are the only place in the universe where heavy elements like gold and platinum can be forged. Every gold ring, every speck of iron in your blood, was cooked up in the heart of a dying star and flung across space by a supernova. You are, quite literally, made of stardust. At the center of this frantic galactic construction site, something even more profound is taking shape. In the densest, most chaotic part of the proto-galaxy, where stars and gas are crowded together, a monster is growing. A supermassive black hole. We don't know for sure how these cosmic titans form. That's another one of those scientific debates that could easily turn into a heated argument at an astronomy conference. One idea is that they started from the collapse of one of those first-generation monster stars, leaving behind a seed black hole that just kept feeding. Another theory suggests they formed from the direct collapse of a gigantic gas cloud, skipping the star phase entirely. Whatever their origin, they grow by devouring anything that gets too close: gas, dust, and entire stars. As you watch, you see a stream of gas get pulled towards the galactic center. It doesn't fall straight in. Instead, it forms a swirling, flattened disk around the black hole, an accretion disk. The friction and gravitational shear in this disk heat the gas to millions of degrees, causing it to shine more brightly than all the billions of stars in the galaxy combined. This incredibly luminous object is a quasar. In this early stage of the universe, many galaxies have these brilliant quasars at their hearts, shining like cosmic lighthouses across the vastness of space. They are so bright we can still see them today, even though they are billions of light-years away, giving us a direct window into this turbulent era. For hundreds of millions, even billions of years, this is the way of the universe. Galaxies grow through a series of messy mergers. Smaller galaxies are gobbled up by larger ones in a process called galactic cannibalism. It sounds brutal, but it's how galaxies like our own Milky Way were built. Our galaxy contains stars and star clusters that were once part of other, smaller galaxies that we absorbed over cosmic time. As you drift through this maturing universe, you start to see more familiar shapes emerge. The chaos is beginning to subside. Through these countless mergers and the slow, steadying hand of gravity and rotation, some galaxies start to flatten out into majestic spiral disks. The clumpy, irregular blobs are evolving into the elegant structures we know today. The universe is starting to look, well, more like itself. Here's a quirky little fact about this era: some of these early galaxies were surprisingly dusty. The sheer rate of supernova explosions produced vast quantities of carbon and silicon dust grains. Some of the most distant galaxies we see with our modern telescopes are so enshrouded in this dust that they are almost invisible in normal light, but they glow intensely in the infrared. They are like cosmic ghosts, hiding their brilliant starbursts behind a veil of their own making. The universe is now a few billion years old. The cosmic web is well defined, with galaxies strung along its filaments like jewels on a necklace. The frantic, chaotic youth of the cosmos is giving way to a more stately, mature middle age. Quasars are starting to quiet down as their fuel supply dwindles. Star formation rates are slowing to a more sustainable pace. Out in a quiet, unassuming spiral arm of one of these newly formed, elegant galaxies, a galaxy we will one day call the Milky Way, a particular cloud of gas and enriched dust is starting to feel that familiar, gentle pull of gravity. It's a nondescript cloud, one of billions. But it contains the specific stardust, the specific blend of elements, that will become our home. The galactic stage is set. Now it's time to zoom in on our own little local drama. The birth of our solar system is next. You've traveled across billions of years and witnessed the birth of the universe, the first stars, and the grand assembly of galaxies. Now, let's bring our focus a little closer to home. We're in a quiet, suburban spiral arm of a fairly average galaxy called the Milky Way. The time is roughly 9 billion years after the Big Bang, which means the universe is about 2/3 of its current age. The wild, chaotic galactic mergers have mostly settled down. Our galaxy has taken on its familiar, graceful spiral shape. Here, in this relatively peaceful neighborhood, you see a vast, cold, and dark cloud of gas and dust. It's a nebula. A stellar nursery. It's dozens of light-years across, and it's composed of the recycled remnants of countless generations of dead stars. There's hydrogen and helium from the Big Bang, of course, but it's also richly seasoned with carbon, oxygen, iron, silicon, and even trace amounts of gold and uranium. It's a cosmic treasure chest of raw materials. For a long time, this cloud just drifts. But then, something gives it a nudge. Perhaps a shockwave from a nearby supernova explosion passes through it, compressing the gas. Or maybe it's just the cumulative, patient pull of its own gravity finally reaching a tipping point. Whatever the cause, the cloud begins to collapse. As it collapses, it starts to rotate, just like a figure skater pulling in their arms to spin faster. The cloud flattens out into a massive, spinning disk. This is the solar nebula. It's a bit like a cosmic pizza dough being spun in the air. Most of the material, over 99.8% of it, spirals down into the center. The pressure and temperature there build relentlessly. It gets hotter and hotter, denser and denser, until, you know the drill by now. Nuclear fusion ignites. A new star is born. Our sun. At this point, our young sun is a bit of a messy, temperamental star. It's surrounded by this swirling disk of leftover gas and dust, and it's blasting out a powerful solar wind, a stream of charged particles that pushes a lot of the lighter gas away from the inner part of the disk. This process creates a gradient within the disk. Closer to the sun, where it's hot, only materials with very high melting points can survive. Things like rock and metal. Further out, in the colder regions beyond what's called the frost line, it's cool enough for volatile compounds like water, ammonia, and methane to freeze into tiny ice particles. This simple separation is the key to why our solar system looks the way it does. Now, a new process begins, accretion. Tiny dust grains and flecks of rock and metal in the inner disk start to stick together. First through electrostatic forces, like dust bunnies under your bed. They form slightly larger clumps. These clumps then collide and merge, growing bigger and bigger. It's a slow, messy, and frankly, random process. Pebbles become rocks, rocks become boulders, boulders smash together to form kilometer-sized objects called planetesimals. You're floating in this chaotic construction zone. It's a cosmic demolition derby. Planetesimals are constantly crashing into each other. Some collisions are destructive, shattering the objects back into smaller pieces. But others are constructive, allowing them to merge and grow larger. The biggest of these planetesimals, the ones that get a head start, become the winners. Their gravity grows stronger, allowing them to pull in more and more material, clearing out their orbits. These are the protoplanets. In the hot inner solar system, 4 of these rocky protoplanets eventually emerged as the dominant bodies: Mercury, Venus, Earth, and Mars. They are dense, made of rock and metal, because that's all that could solidify this close to the sun. Way out past the frost line, the same process is happening, but with an extra ingredient: ice. Since ice is so much more abundant than rock and metal, the protoplanets out here can grow much, much larger. They become so massive that their gravity is strong enough to capture the vast amounts of hydrogen and helium gas left over in the outer disk. They swell into colossal gas giants. This is how Jupiter and Saturn were born. They have a small, rocky, or icy core deep inside, though the exact nature of Jupiter's core is still a matter of scientific debate, with some models suggesting it might be a fuzzy, diluted core rather than a solid ball, but the vast majority of their bulk is a thick, swirling atmosphere of hydrogen and helium. This brings us to a mind-boggling little fact about Jupiter: despite being a gas giant, it has the most powerful magnetic field of any planet in our solar system, which creates auroras at its poles that are thousands of times more powerful than Earth's. These auroras are so intense they emit X-rays, something we don't see in the northern or southern lights here. The outermost planets, Uranus and Neptune, are a bit different. They formed even further out, where the disk was thinner and the accretion process was slower. They didn't get quite as massive as Jupiter and Saturn, so they didn't capture as much hydrogen and helium. They are primarily composed of those frozen volatiles, water, ammonia, methane, which is why they are often called ice giants rather than gas giants. The methane in their atmospheres is what gives them their beautiful blue hues. The solar system is now about 100 million years old. It has taken shape, but it's still a wild and untamed place. The planets are there, but their orbits aren't all stable yet. The space between them is filled with leftover debris, asteroids and comets. The late stages of planet formation were a period of intense bombardment, as the giant planets, especially Jupiter, gravitationally scattered this debris all over the solar system. This late heavy bombardment would have profound consequences for the rocky inner planets, especially the one that was just the right distance from the Sun, a small, bluish-green world that was about to have a very rough childhood. Let's zoom in further, past the orbit of Mars, and fix our attention on the third planet from the Sun, Earth. Or, as it was back then, Proto-Earth. It's not the serene blue marble you know. What you see is a terrifying, magnificent, and utterly alien world. It's a molten ball of rock, glowing a dull, angry red. The surface is a roiling ocean of magma, thousands of degrees hot. There is no solid ground, no water, no air. The atmosphere, such as it is a toxic, suffocating mix of carbon dioxide, nitrogen, and water vapor, blasted out from the planet's interior by constant, planet-wide volcanic eruptions. This is Earth in its Hadean Aeon, a name fittingly derived from Hades, the underworld. It's a world being forged in fire. The heavier elements, like iron and nickel, are sinking through the molten rock, drawn by gravity to the planet's center to form the metallic core. This process, called differentiation, is crucial. It's what will eventually give Earth its magnetic field, a protective shield that will one day fend off the harsh solar wind and allow an atmosphere to remain. You are witnessing a planet in the throes of its violent, chaotic birth. The solar system is still a messy construction site, littered with leftover planetesimals. And for the young Earth, the biggest impact is yet to come. Floating in a nearby, but unstable, orbit is another protoplanet. A body roughly the size of Mars, which scientists have posthumously named Theia. Its orbit, perturbed by the gravitational dance of the other planets, crosses Earth's path. And one day, they collide. It's not a direct, head-on smash. It's a cataclysmic glancing blow. Theia strikes Earth with unimaginable force, an impact that makes 1,000 nuclear bombs look like a firecracker. The crust of both planets vaporizes instantly. A colossal plume of molten rock and superheated vapor is ejected into orbit around the Earth. Theia itself is obliterated, its iron core sinking into Earth's own, merging with it. You watch from a safe distance as this ring of incandescent debris circles the wounded, now even hotter, Earth. Over a surprisingly short amount of time, maybe only a few thousand years, a blink of an eye in cosmic terms, the debris in this ring begins to clump together. It accretes, just as the planets did, forming a single, large, spherical body. The Moon. This giant impact hypothesis is the leading theory for the Moon's origin, and it explains a lot. It explains why the Moon is so large relative to its parent planet, why it's made of rock that's compositionally very similar to Earth's mantle, and why it has such a tiny iron core. Our Moon is, in essence, a child of this cosmic collision, born from the shattered remnants of Earth and Theia. And its presence will be profoundly important for the future of our planet. It will stabilize Earth's wobble, preventing wild climate swings, and its gravitational pull will create the tides, a rhythmic sloshing of the oceans that may have played a role in the origin of life. The Earth slowly recovers from this colossal impact. Over millions of years, the magma ocean begins to cool. A crust starts to form on the surface, a fragile, dark skin of basaltic rock. But it's a precarious piece. The crust is constantly being fractured and recycled by intense volcanism and the remaining rain of smaller asteroids and comets from the late heavy bombardment. And it's this bombardment that delivers a crucial gift. These comets and asteroids, which formed in the colder, outer regions of the solar system, are rich in water ice. For millions of years, they pelt the young Earth, delivering water, molecule by molecule. As the planet's surface continues to cool below the boiling point of water, the steam that has been shrouding the planet in a thick, dense atmosphere begins to condense. And then, it begins to rain. It's not a gentle shower. It is a torrential, planet-wide downpour that lasts for centuries, maybe even millennia. Water pours from the skies, filling the craters and basins, running in vast rivers over the newly formed volcanic rock. The first oceans are born. They are not the blue, salty seas of today. They would have been hot, acidic, and probably a brownish-green color due to a high concentration of dissolved iron. So, here you are, floating above a world that is finally starting to look a little more familiar. It's a water world, covered almost entirely by a global ocean, dotted with the peaks of towering volcanoes sticking out like islands. The sky is a hazy orange-pink, thick with carbon dioxide and nitrogen, with no free oxygen to speak of. The sun, shining through this thick haze, would appear dimmer and redder than it does today. It's a strange, stark, and still very hostile planet. But it has all the key ingredients now: a stable orbit, a protective moon, a solid crust, and liquid water. It's a stage, perfectly set. But it's an empty one. The planet is sterile. Lifeless. But deep in these warm, murky, chemical-rich primordial oceans, perhaps near the scalding, mineral-belching vents on the seafloor known as hydrothermal vents, something new is about to stir. The leap from geochemistry to biochemistry is about to be made. The quiet, unassuming start of life is on the horizon. The Earth is now a world of water and rock, bathed in the faint light of a young Sunday. It is restless, with volcanoes spewing gas and lava, and a thick, oxygen-poor atmosphere. For hundreds of millions of years, it is just this, a beautiful, but sterile, chemical laboratory. The oceans are a primordial soup, a rich broth of organic molecules delivered by comets and asteroids, and synthesized by lightning in the atmosphere and chemical reactions at deep-sea hydrothermal vents. You have carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, all the basic building blocks of life, sloshing around in a planet-sized beaker. But having all the bricks doesn't mean you have a house. The leap from a collection of non-living organic molecules to the first living, self-replicating cell is arguably the biggest mystery in all of science. It's such a monumental step that we're not even sure where or how it happened. Was it in a warm little pond, as Darwin speculated? Was it in the scorching, mineral-rich water jetting from hydrothermal vents deep on the ocean floor? Or maybe in the clay deposits of ancient beaches? This is a question where even the most brilliant scientists will tell you, with a refreshing dose of humility, that they are still piecing together the puzzle. We just don't know for sure. It's the ultimate cold case. But somehow, somewhere on this young planet, it happened. A collection of molecules, perhaps fatty lipids forming a primitive bubble or membrane, enclosed a set of other molecules that could, by chance, make crude copies of themselves. This was the first replicator. It wasn't life as you know it. It was more like a chemical machine, a fragile protocell that just happened to have the knack for making more of itself from the raw materials around it. This is the moment life quietly, almost invisibly, enters the story. You wouldn't have seen a flash of light or heard a chorus of angels. It would have been a silent, microscopic event in a murky corner of a vast ocean. But it was the most important event in Earth's history. For the next billion years, maybe more, life remains incredibly simple. The only inhabitants of this planet are single-celled organisms, similar to modern bacteria and archaea. They are microbes, living in the oceans, consuming chemicals for energy. The planet's surface, the continents, remain barren and empty. It's the boring billion, as some paleontologists cheekily call it. An eon where not much seemed to change on the grand scale. But beneath the surface, a quiet revolution is brewing. One group of these bacteria, called cyanobacteria, develops a revolutionary new trick. They figure out how to harness the energy of sunlight. Photosynthesis. They take in carbon dioxide and water, and use sunlight to convert them into energy, releasing a waste product in the process. That waste product is oxygen. At first, this newly produced oxygen doesn't build up in the atmosphere. It immediately reacts with the dissolved iron in the oceans, causing it to rust and precipitate to the seafloor. Over millions of years, this process lays down vast deposits of iron ore, creating formations known as banded iron formations. Most of the iron mined by humans today comes from these ancient layers of rust, laid down by trillions of microscopic bacteria. A quirky thought, the steel in your car is, in a way, a fossil of the first planetary-scale air pollution event. Eventually, after all the iron in the oceans is used up, the oxygen finally starts to bubble out of the water and accumulate in the atmosphere. This is the Great Oxidation Event. And for the majority of life on Earth at the time, which had evolved in an oxygen-free environment, it was a catastrophe. Oxygen was a toxic, corrosive poison. It caused a mass extinction, wiping out countless species of anaerobic microbes. But life is resilient. Some microbes retreated to oxygen-free pockets, where their descendants still live today. Others, however, evolved to not only tolerate oxygen but to use it. They developed a new, far more efficient way to get energy, aerobic respiration. This was a game changer. The energy payoff from respiration is huge, and it paved the way for more complex, energy-hungry life forms. And one of the most significant steps towards that complexity happened in another one of those quiet, microscopic events. One simple cell, for reasons we can only guess at, engulfed another. But instead of digesting it, it formed a partnership. The engulfed cell became a specialist, a dedicated power plant for its host. This was the birth of the mitochondrion, the energy-producing organelle inside your own cells. This event, the theory of endosymbiosis, is what gave rise to the eukaryotic cell, the complex cell type with a nucleus and other internal structures that all plants, fungi, and animals, including you, are made of. The stage is now set for a new explosion of diversity. The boring billion is over. The Earth is now oxygenated, the oceans are clearing, and life has the energetic toolkit it needs to get bigger and more complex. You're floating over a planet that has been fundamentally reshaped by its tiniest inhabitants. The air you will one day breathe, the iron you will one day build with, the very cells in your body, all owe their existence to these ancient, microscopic pioneers. Life isn't just a passenger on this planet, it's a geological force in its own right, sculpting the world to its own design. And now, with the advent of complex cells, evolution is about to pick up the pace, leading to the first tentative experiments with multicellular animals, swimming in the cold, dark waters below. The stage is set. The Earth has oxygen, complex cells with their tiny mitochondrial power plants, and vast oceans. For a while, life remains a quiet affair of slimes and mats and simple, soft-bodied creatures drifting in the dark. But then, about 540 million years ago, evolution seems to drink 3 espressos and get to work. This is the Cambrian explosion. Over a geologically brief period of just a few tens of millions of years, the blueprints for almost all major animal groups we know today appear in the fossil record. It's an explosion of diversity. You're now swimming in seas teeming with strange and wonderful creatures. There are trilobites scuttling along the seafloor, looking like armored woodlice. There are bizarre, shrimp-like predators with grasping claws, and alien-looking creatures with 5 eyes. It's like evolution opened its sketchbook and just tried every weird idea it could think of. After this initial burst of creativity, life begins its next great conquest, the land. For billions of years, the continents have been barren, sterile deserts of rock. Now, the first green shoots of primitive mosses and liverworts begin to cling to the damp edges of the water. They are the pioneers, slowly, painstakingly creating the first soils. Following them, about 400 million years ago, are the animals. The first to venture out are likely scorpion-like arthropods, and soon after, insects. Then, a fish, perhaps seeking to escape a predator or find a new food source, uses its sturdy, lobe-like fins to haul itself onto the shore. This clumsy, gasping creature is your distant ancestor. The world is now green and alive. Vast forests of giant ferns and horsetails cover the land, raising oxygen levels to new heights. Giant dragonflies with 2-foot wingspans buzz through the humid air. Amphibians give way to reptiles, who develop the amniotic egg, a private little pond that allows them to break their final tie to the water and conquer the dry interiors of the continents. But life on Earth is not a simple, straight line of progress. It is punctuated by brutal setbacks. The greatest of these, far worse than the one that killed the dinosaurs, occurs about 252 million years ago. The Permian-Triassic extinction event, or the Great Dying. We're not entirely sure what caused it. Massive volcanic eruptions in Siberia are the prime suspect, but it was a planetary catastrophe. It wiped out an estimated 96% of all marine species and 70% of terrestrial vertebrate species. Life on Earth came terrifyingly close to being completely extinguished. It was the planet hitting the reset button. From the ashes of this devastation, a new group of reptiles rises to dominate the recovering world. The dinosaurs. For the next 165 million years, they are the undisputed kings. From the colossal, long-necked sauropods to the terrifying Tyrannosaurus rex, they fill every ecological niche. While they reign, another group of creatures exists in their shadows. They are small, furry, nocturnal, and shrew-like. They are the first mammals. Your ancestors. They spend their time hiding, scurrying, trying not to get stepped on. And then, 66 million years ago, the sky falls. A 6-mile-wide asteroid, traveling at tens of thousands of miles per hour, slams into the coast of modern-day Mexico. The impact releases more energy than 1 billion nuclear bombs. It triggers global earthquakes, tsunamis, and firestorms. A cloud of dust and soot blankets the earth, blocking out the sun for years, plunging the world into a long, cold, dark winter. The dinosaurs, with their massive food requirements, cannot survive. They perish, along with 3/4 of all species on Earth. But in the rubble of this fallen world, the meek inherit the earth. The small, adaptable mammals survive. With the great reptiles gone, a world of opportunity opens up. They diversify, growing larger, smarter, spreading across the globe. Among them, a group of primates takes to the trees, developing grasping hands, forward-facing eyes for depth perception, and larger brains. Much later, in the grasslands of Africa, a changing climate forces some of these primates down from the trees. They begin to walk on 2 legs, freeing their hands to carry things, to make tools. Their brains grow larger. They harness fire. They develop language. They begin to cooperate in complex ways. And somewhere in this chain of events, something utterly new and mysterious emerges. Consciousness. The simple awareness of the world blossoms into self-awareness. A mind that cannot only experience the world, but can ask questions about it. Why is the sky blue? What are the stars? Where did all this come from? This is the great unanswered question, the so-called hard problem, that science and philosophy still grapple with. How does a collection of electrified cells in a brain give rise to the rich, subjective experience of being you? We simply don't know how matter becomes mind. And that brings us to the end of our journey. All the way from that infinitesimal point of nothing and everything, through the dark ages, the first stars, the galactic factories, the birth of a small rocky planet, the quiet stirring of the first cell, the rise and fall of great beasts, to this very moment. You. Lying here, in the quiet of the night. You are the product of 13.8 billion years of cosmic evolution. The iron in your blood was forged in the heart of a dying star. The water in your cells was delivered by comets. The atoms in your body are the same atoms that were present in that primordial fog. You are, in the most literal sense, stardust. Stardust that has, through an improbable and epic journey, learned to think, to feel, to wonder, and to look back at the universe and marvel at its own origin story. The universe, through your eyes, is finally becoming aware of itself. The journey is complete. The vast, cosmic story has led to this quiet, simple moment. Your moment. The universe has done its work for now. The epic of creation, of destruction and rebirth, of stars and of life, has settled, like dust motes in a sunbeam, into the gentle peace of your room. The great celestial river has flowed to this calm, still shore. Feel the weight of your body, a small, warm anchor in the vastness of spacetime. You are a part of this story, a precious, thinking piece of the cosmos. The hum of the fan, the gentle rustle of your blankets, these are the sounds of your own small galaxy, spinning quietly through the night. With every slow breath you take, imagine yourself breathing in the faint, ancient light of the stars. And with every slow breath out, feel the day's tensions dissolve, releasing back into the endless, patient dark. You don't need to hold on to the story anymore. It is a part of you now. Let it fade into the background, like the soft glow of a nebula seen from a great distance. The cosmic tide is pulling you gently now, out into the quiet sea of sleep. There are no more explosions, no more collisions, only the deep, silent, rhythmic pulse of the universe at rest. Let your mind drift. Let your thoughts soften and blur. You are safe. You are stardust. And it is time to dream. Dream of starlight and silent seas, of ancient suns and the quiet miracle of being here.